everyone, and welcome to this action potential rapid review. To start with, let's take a look at the anatomy of a neuron. A neuron has a large nucleus which contains the nucleolus and chromosomes, which are necessary for the production of coded proteins within the cell. The cell body contains abundant rough endoplasmic reticulum and a well-developed Golgi apparatus for protein synthesis. Dendrites receive the majority of synapses. Their morphology can vary quickly. The axon hillock is the area where there is the highest concentration of voltage-gated ion channels and acts as the trigger zone for action potentials. Axons transmit information. The membrane is organised into specific domains to maintain high-speed conduction. A large number of mitochondria are required to maintain the membrane potential. The myelin sheath is a fatty layer which insulates the axon, much like the rubber coating on an electric wire. The nodes of Ranviers are gaps in this myelin sheath and facilitate the rapid conduction of action potentials. Schwann cells are responsible for the production of myelin in the peripheral nervous system. The equivalent in the central nervous system is the oligodendrocyte. And finally, the axon terminal. Neurons often branch extensively close to the target. The terminals can take the forms of boutons or varicosities. The resting potential across the cell membrane is approximately -70 millivolts, with higher concentrations of sodium outside the cell and higher potassium inside. The threshold potential is around -55 millivolts. This is the potential which needs to be reached to trigger an action potential. A stimulus causes the sodium channels to open and the cell to become more positive. If the membrane potential fails to reach the threshold of -55, then it will fail to initiate an action potential as demonstrated here. Depolarization. Once the action potential has been triggered, sodium channels open, resulting in a rapid influx of sodium ions, and the cell becoming less negative. Next, the sodium channels close and potassium channels open. The efflux of potassium causes a drop in the membrane potential, leading to repolarization. The potassium channels are slow to close, which causes the hyperpolarization you can see here, dropping below the resting potential. The resting potential is re-established by exchange pumps, which move sodium ions in and potassium ions out. Let's review the key points of this process. Resting potential. Potassium ions are concentrated inside the cell. They can enter and exit based on electrochemical forces, but membrane potential remains constant. Depolarization. Sodium ion channels open in response to a stimulus. Sodium ions rush into the cell, making it less negative. Repolarization. Sodium channels close and potassium channels open. Potassium ions rush out of the cell, allowing positive charges to leave. And finally, resting potential re-established. Sodium and potassium ion channels are now closed. The exchange pump moves sodium ions out and potassium ions in to maintain membrane potential. Let's now take a look at how the action potential spreads along the length of the axon. In a myelinated axon, the action potential moves down the axon in a process called saltatory propagation. In this process, the current generated by the action potential jumps from one node of Ranvier to the next. In an unmyelinated axon, like the one shown here, the action potentials move by continuous propagation. The moving action potential affects one section of the neuron at a time, with each then depolarizing the next to its threshold potential, resulting in the opening of sodium channels and depolarization. This cycle repeats down the length of the axon.
Find us on Facebook, Instagram, and subscribe to our YouTube channel to help explain the mysteries of the brain.